everybody, how's it going today? In this video we're going to look at half-lives and radioactive decay series. Our goals for this video are to describe the concept of a half-life and explain how it applies to radioactive decay and radioisotopes. We'll also look at some basic forms of half-life calculations, as well as how the half-life of certain elements can be used in the process of radioactive dating, which helps determine the age of rocks and other geologic formations. Lastly, we'll look briefly at the decay series of uranium-238, which is a wonderful example of radioactive decay series. For starters, what is a half-life? Aside from being a video game series that will totally eventually see a third release, half-life in chemistry refers to the amount of time it takes for half of a sample or radioactive material to decay and form products. After one half-life, half of a sample will have decayed and half will remain unchanged. After another half-life, 3/4 will have decayed and 1/4 will still remain. After a third half-life, you'll be left with 1/8 of your initial sample, and then a 1/16, and so on and so forth. Each radioactive isotope has its own unique half-life, which can range from millions of years to microseconds. The half-life of a substance is useful for determining how long it will take for the breakdown or formation of a product or substance. It can also be used to determine how long a sample has been decaying, which we'll look at in more detail a bit later. The simplest formula used for half-life reactions is that the amount of your sample left at the end, or your final sample, is equal to the amount of your sample you started with, your initial sample, times 1/2 to the n, where n is the number of half-lives that have passed. This is probably best understood through an example, so let's look at how we can use this in action. So for our example problem, this says that nitrogen-13 decays via radioactive decay to form carbon-13 with a half-life of 10 minutes. This is actually a form of positron decay, which is something we haven't talked about yet, but that's not really the important part here. So we have a half-life of 10 minutes, and the first part is, how long will it take for 4 half-lives to pass? Now, this is actually kind of a trick question. Really, all we need to know here is that the half-life, TH, equals 10 minutes. We want 4 times the half-life, which equals 40 minutes. So that one's pretty, oh, I can't spell. That one's pretty simple. It's just multiplying it by 4. The second one is where we actually need to use our formula. It says if you start with a sample of 2 grams of nitrogen, how many grams of carbon will be present after 30 minutes? Now, we know that 30 minutes, I really can't spell the word minutes today. 30 minutes equals 3 half-lives, since each one is 10 minutes apiece. And we could do that mathematically, but that's pretty simple. So we've got a half-life, 3 half-lives is our n, and our initial sample is 2.00 grams, right? So 2.00 grams times, actually here, let's write out the full formula. Sample final equals sample initial times 1/2 to the n. So in this case, we've got our final equals 2 grams, which is our initial sample, times 1/2 to the third, which equals 2 times 1/8, which equals 0.25 grams. And then we can check that by saying, okay, if we start with 2, after 1 half-life, we're going to be 1/2 of that, so we'll be at 1. After 2 half-lives, we'll be at half of that, which will give us 0.5. And after 3 half-lives, we'll be at half of this, which will give us 0.25, which is what we got. The most common use of half-lives in the real world is for radioactive dating. Radioactive dating requires a few different properties from the radioactive material being used, but 2 of the major radioisotopes used in radioactive dating are uranium-238 and carbon-16. Uranium-238 is especially useful for looking at the ages of very old rocks, as it has a half-life of 4.5 times 10 to the 9th, or 4.5 billion years. Uranium-238 decays to form lead-206, which is stable. By comparing the ratio of uranium-238 to lead-206, scientists can infer the approximate ages of rocks as old as our solar system, which is about 4.6 billion years old. Uranium-238 decaying to lead-206 happens over the course of a bunch of different decays, which together are referred to as a decay series. The decay series is shown here on the right, with the different intermediates, their half-lives, and the type of decay, either alpha or beta, they undergo to form the next product. If you look closely, you'll notice that most of the elements in this decay chain have more than one isotope present. You'll also notice that the half-lives vary wildly, from 4.5 billion years to orders of days, minutes, or even microseconds. Perhaps the most concerning intermediate form in terms of human health hazards in this decay chain is radon-222. Radon is a noble gas, and as a gas at normal temperatures and pressures, it can actually seep out of the ground, where most of the uranium is initially present, and into the air, where it can be inhaled by humans or other animals. If radon happens to decay in the lungs, it will change into polonium, which is a solid, and will be difficult to expel. This results in multiple radioactive decay processes happening inside the lungs, which can cause serious health hazards like cancer. This is why radon detectors are often used to detect radioactive elements, as opposed to testing for the uranium itself. It is worth noting that uranium is not the only naturally occurring element that undergoes a decay series, but this is one of the most extensive. Let's review. A half-life is the time it takes for 1/2 of a sample of radioactive material to decay and form products. Different radioisotopes have different half-lives, ranging from microseconds to millions or even billions of years. Half-lives can be analyzed using the formula amount of final sample present equals the amount of initial sample present times 1/2 to the n, where n is the number of half-lives passed. We use this analysis of half-lives to perform radioactive dating, which allows us to determine the age of rocks and other geologic formations. Uranium-238, commonly used in radioactive dating, goes through a decay series with numerous intermediates, ultimately resulting in the formation of the stable isotope lead-206. Radon-222 is the most dangerous intermediate in this decay series, primarily because of its natural gaseous state and its relatively short half-life. That's it for today's video. Thanks for watching, and I'll see you next time.